Swayam Prabha. Digital India. Educated India.
Now, why this is called variance inflating factor? Because from here you can understand, if the r square tends to be, if the r square j tends to 1, then what will happen? Variance of beta j will tend to infinity, isn't it? Variance of beta j will tend to infinity. That is why this 1 by 1 minus r square j is called the variance inflating factor. Okay? If there is high degree of linear dependence among several explanatory variable, that means you can expect r square j would be quite high, and if r square j tends to infinity, then tends to 1, you will get variance of beta j tends to be infinite, okay, tends to be infinite. So, that means this is a serious consequence. So, what will happen? That means variance of beta j, beta hat j, as I told you, this is sigma square divided by summation x j square into 1 minus r square j, and when r square j tends to 1, variance of beta j tends to infinite, and if you plot r square in this axis and variance of beta hat in the y axis, then you will see the relationship will look like this, So, as r square increases, you will get this type of relationship, it will increase like anything, okay, this type of relationship. Now, when variance increases, variance of beta j increases, that will lead to the standard error of beta j also will increase. The standard error of beta j will also increase, and if standard error increases of beta hat, what will happen to the t statistic, which is nothing but beta hat j divided by standard error of beta j. What will happen? If this increases, then t statistic will fall drastically. So, t statistic will become insignificant. So, that means in presence of multicollinearity, what you observe as the t value, that is actually not the actual t value, because the variance got inflated in presence of MC, standard error got inflated in presence of FC. That means this t statistic appears to be artificially low, and if the t statistic is low, then what will happen? You will see that your individual t statistic is insignificant, so that means variables will appear to be insignificant. Okay, but even though these t statistics, individual t statistics are insignificant, you will still get a high r square, because that is coming from here. So, that means what would be the consequence of multicollinearity? Suppose this is your model yi equals to alpha plus beta 1 x 1 I plus beta 2 x2I plus ui, and you see by individual t statistics, let us say this is T1 and this is T2, both are insignificant in presence of MC. But the R square what you get from this model, R square will be quite high. So, this is the classic symptom as well as consequence of multicollinearity. So, that means many of your explanatory variables will appear to be insignificant, but still you see the high R square value from the model. So, whenever you get this type of result, you estimate a model and immediately after estimation you see that your R square is quite high, but many of your explanatory variables are insignificant individually, then immediately it should click in your mind, that means my data is suffering from multicollinearity problem. This is the classic symptom as well as consequences of multicollinearity problem. This will happen, right? Okay. So, that means your variance will get inflated. I will write shortly consequences, variance and standard error will get inflated in presence of MC, multicollinearity, and as a result of which you will get insignificant t statistics for the explanatory variable, but high R square. So, these are the two consequences of multicollinearity. So, that means out of the three desirable properties, consistency and unbiasedness properties are still maintained, but efficiency property gets disturbed. And when I say efficiency, it means for a given sample, the variance of a particular beta hat, let us say beta j, if you assume beta j is correlated with other variable, may get disturbed, and that will result in this type of situation. This is the classic consequence as well as symptom of multicollinearity problem, right? Multicollinearity problem. Now, what you will do when you have these are the consequences, then the next question is, how will you detect multicollinearity, detection of multicollinearity? Detection of multicollinearity. First, this is a simple measure. You just do what you do, check pairwise correlation. Check pairwise correlation among the explanatory variable. For example, let us say my model is yi equals to, let us say, beta 1 plus beta 2 x 2I plus beta 3 x 3I plus beta 4 x 4I plus ui. Then the simple measures that they say when you write a paper also, before presenting your regression result, what you show actually in your paper, what is the pairwise correlation between x2, x3, x3, x4 and x1, x2, x4. So, this is called pairwise correlation, and the statistical software what we use, if you simply, after importing the data, if you simply put the stata command which is CORR, then x2, then x3 and x4, if you put this command, this is the stata command, then that will give you this pairwise correlation. Okay, pairwise correlation, and any pairwise correlation which is 0.8 or more than 0.8, that means when R pairwise correlation, let us say between 2 3 equals to 0.85, or let us say R 2 4 is 0.81, or let us say R 3 4 equals to 0.90. So, these are basically high pairwise correlation. So, if you get this type of result, then you will understand that there is some kind of multicollinearity problem in our data set, and we must rectify that. But this is a simple measure. As I said, that pairwise correlation is not a very rigorous statistical measure of detecting multicollinearity, because this is only a simple pairwise correlation measure, and it has some limitation also. It has some limitation. For example, let us say I am assuming that this x4 is highly correlated with x2 and x3. That means, let us say lambda 1 x, there is perfect linear dependence, lambda 2 x 2I minus lambda 3 x 3I minus lambda 4 x 4I equals to 0. Okay, there is perfect linear dependence. So, what we can expect from this relationship? From this relationship, we can expect that r square 4 equals to 1. So, that means when I am regressing the fourth explanatory variable on the second and third explanatory variable, the r square from this model is coming out to be 1. Okay. But if you write this formula, what is r square 2 3 actually? R square 4 2 3 is basically r square 4 3 plus r square 4 2 minus 2 into r square, sorry, this is not r square, this is r 4 3, then r 4 2, then r 2 3, 1 minus r square 2 3. So, that means if you substitute 1 here, so for 1 this is r square 4 3 plus R square 42 minus 2 into R 43 R 42 R 23, this is 1 minus R square 23, where R square indicates the squared correlation, or you can say that by regressing the fourth variable on this, and this is partial correlation coefficient. Now, if these relations to be satisfied, so that means if these relations to be satisfied, then what you can understand is that from there, if you just look at this relationship carefully, okay, look at this relationship carefully, that this left hand side is 1 and you need to have specific value for this. Now, this relation if you look at, even for R square, even for R square 4 R 42, if you assume 0.5 and R 43 is also 0.5 and R 23 is minus 0.5, you will get this condition to be satisfied. Okay? This condition to be satisfied. That means pairwise correlation, if you see, it is not very high, but still you have high degree of multicollinearity. So, that is why I said that pairwise correlation may not always guarantee, that means low pairwise correlation does not always rule out the possibility of multicollinearity problem. That is why this is not a very rigorous statistical measure, because from this relationship what I see, that even though R square 423 is quite high, that means when R square 423 is 1, from you have serious multicollinearity problem. Fourth explanatory variable is perfectly linearly dependent on 2 and 3. Second and third variable perfectly explain the fourth explanatory variable. But from the partial pairwise correlation, we see they are only 0.5. So, that is why it may not, if the pairwise correlation is quite high, then you will understand there is multicollinearity problem, but if they are low, they do not rule out the possibility of multicollinearity problem. We have to check for some other measure. And what is the other measure that is simple to apply also? That is VIF. That means 1 minus 1 by 1 minus R squared G. Okay. This is the other way of detecting this. So, if the VIF, so defined, if the VIF is greater than 10 for this particular jth variable, that will imply that the jth variable shows MC. That means jth variable is perfectly linearly dependent with others. So, this is a simple formula to apply, and it is very easy to estimate from the statistical software also. And third one is, as I said, how will you detect that many of the explanatory variable are individually insignificant as T statistics are insignificant but high R square. So, this will also help you detecting multicollinearity in your data set, okay, in your data set. Okay. So, that means we have discussed the consequences of multicollinearity, and this is how you can detect multicollinearity. And next thing what we need to do is, the solution for multicollinearity. What to do? What to do to solve MC, multicollinearity, okay, to solve multicollinearity. Now, in this context, econometricians, they generally say that multicollinearity is a sample problem. Okay, what I am saying, this is a very, very important statement I am making. They say that multicollinearity is a sample problem. It's a sample problem. So, that means we need to modify our sample appropriately to solve the multicollinearity problem. I will explain this. Let us say that your model is consumption equals to alpha plus beta 1 income, this is I income, plus beta 2 wealth. Okay, wealth. So, when I include both income and wealth in my model to estimate the consumption function, that means what we assume? We assume that in population, income and wealth are actually not correlated. But in sample, what is happening here, it may so happen in sample, the sample what you have collected, then you got information from those individuals who are having. So, in sample, individuals are having high income with high wealth as well. So, that means even though in population we assume income and wealth to be not correlated, because that is how consumption function theory says that consumption depends not only individual's income but also wealth. We assume in the population they are not correlated, but when we collect a sample, it may so happen that individuals are having high income with high amount of wealth as well. So, how will you solve this problem? To solve this problem, you need to collect a sample wherein there are individuals. So, what is the solution? What is the solution? In our sample, we should have individuals with higher income but lower wealth and higher wealth but lower income. So, we need to design our sample in such a way that this particular property is satisfied. We have individuals which are having high income but low wealth, and we have other individuals who are having low income but high wealth. Okay? So, we need to solve this problem by designing the sample strategy appropriately. That is why they say that multicollinearity is basically a sample problem. But it is not always possible to get that type of sample. And how will you get this sample? Just to increase your sample size. Increase your sample size. If you increase your sample size, then you have higher probability of getting that type of individuals who will have higher wealth, low income, and higher income, low wealth. Okay, low wealth. And increasing the sample size, when you increase the sample size, one more thing happens. Let us see, this is variance of j, let us say beta hat j. What I say, this is equals to sigma square divided by summation x j square and 1 minus r square j. And when you increase, what is x square j? This is x square j is basically, this is summation xj minus xj, sorry, this is capital. So, this is xj minus xj bar whole square. Okay. So, if you increase the sample size, obviously this will also increase. Okay. That is why when this increases, then variance of j will come down. That is why increasing the sample size will solve two problems. You will have individuals with higher income, lower wealth, and lower wealth, high income. At the same time, you are reducing the severity of multicollinearity problem as well, right. Now, there are other ways by which we can solve the multicollinearity problem, and those other measures we will discuss in our next class. Thank you very much.